Today, we are going on a journey into a reality much deeper than what our eyes can see. Quantum mechanics, in its attempt to understand the fundamental building blocks of the universe, often operates in ways that are vastly different from the reality we experience in our daily lives. This world possesses extraordinary and sometimes illogical characteristics, like light being both a particle and a wave. Quantum mechanics is one of the most fascinating fields of science because the rules of classical physics do not apply here. Particles can exist in multiple places at once, as long as we can't pinpoint their exact location. Everything is a probability, a variable influenced by the observer. Now, let's unlock the doors to this quantum world and attempt to understand the secrets of the universe. Double-Slit Experiment. Once, a scientist set out to understand one of the most fundamental mysteries of the universe. He designed a simple experiment to observe how light behaves. A beam of light was directed towards a wall through two narrow slits. The expectation was that light would simply pass through each slit and create a simple mark on the wall. But things didn't go as expected. The light behaved like a wave, spreading across the wall, leaving multiple marks that seemed to overlap, much like ripples in water. At that moment, the scientist realized his observations were pointing to something far deeper. Light wasn't just a particle. It was also a wave. But this was only the beginning. The experiment revealed an even greater secret. When the slits were observed, the light behaved like a particle. The act of looking at the light altered its nature. In that instant, light wasn't just a wave or a particle. It was both, depending on whether or not it was being observed. Here, the greatest mystery of quantum mechanics emerged. Light could be both a wave and a particle. Its true nature seemed to depend entirely on the observer. This realization opened the door to a new way of thinking about reality. And here's the question: if something exists in multiple states when unobserved, how much of our perception of reality is truly real? Maybe, just maybe, everything is shaped by the observer. Perhaps the universe only becomes clear when we focus on it. As you reflect on this, ask yourself, if reality can shift based on observation, then how much of it exists as potential, waiting for us to notice? Could it be that our awareness shapes the very fabric of the world around us? Light, like everything else in the quantum world, reveals that reality is not as fixed as it seems. Now, take a deep breath. Close your eyes. Feel the present moment. Let your thoughts drift to the idea that everything around you, everything you observe, is both a possibility and a certainty depending on your focus. Just like light, reality itself may be shaped by what we choose to observe, and it's in that act of observation that the universe takes form. Schrödinger's cat. Imagine a cat inside a box, but in some sense, this cat is both alive and dead at the same time. How can we understand this? What's really going on? Now, close your eyes and imagine yourself somewhere beyond the physical world, in the realm of a thought experiment. This is the essence of the famous experiment first introduced by the renowned physicist Erwin Schrödinger in 1935, a challenge to the strange and sometimes bewildering nature of quantum mechanics. Schrödinger's cat is a thought experiment used to illustrate the phenomenon known as quantum superposition. In this experiment, inside a box, there is a cat, a radioactive substance, a Geiger counter, an acidic substance, and a hammer. The radioactive substance has a probability of decaying within a certain time frame. If decay occurs, the Geiger counter detects it, triggering the release of the acidic substance, which activates the hammer to kill the cat. If no decay occurs, the cat remains alive. However, the way this process is interpreted in quantum physics is quite different. The radioactive particle can exist in a superposition, being both decayed and not decayed at the same time. And here's where it gets interesting. In quantum mechanics, until a system is observed. It can exist in multiple states simultaneously. That means the cat is both alive and dead until an observer opens the box to check. This might sound illogical, but this is the paradoxical and unconscious truth of the quantum world. Schrödinger's cat goes beyond just a physical situation. It also carries a philosophical depth. What is reality? Does reality involve observation and conscious awareness? Or without observation, is reality a blend of conflicting possibilities? This question is one of the most complex and fascinating inquiries of the human mind. Heisenberg's uncertainty principle, the limits of measuring reality. In the world of physics, there are certain things that seem impossible to fully understand or measure. Heisenberg's uncertainty principle is one of the most intriguing and thought-provoking principles of science, shedding light on such a mystery. Developed by German physicist Werner Heisenberg in 1927. This principle is a deep insight into quantum mechanics. But what does it really mean? Imagine trying to measure both the speed and position of a particle at the same time. According to Heisenberg, this is fundamentally impossible. The uncertainty principle is not merely a measurement problem. It is a fundamental feature of nature itself. Heisenberg argued that trying to simultaneously measure a particle's position and velocity imposes a limit due to the very structure of the universe. In other words, it is impossible to know exactly where a particle is and how fast it is moving at the same time. This is because every measurement inherently changes the natural state of the system. This idea can truly shake us. In classical physics, everything was measurable. But Heisenberg's uncertainty principle reveals that such clarity does not apply in the quantum world. It shows that it is an illusion to think we can obtain absolute knowledge about every aspect of the universe, and that we can never fully grasp the true nature of reality. However, this uncertainty is not a limitation. Rather, it offers us a new perspective on the deep structure of the universe. Scientists continuously work to understand and utilize this uncertainty. For it is a fundamental principle that a particle's nature cannot exist without the observer's intervention. In other words, observation and consciousness are fundamental elements of the quantum world. Quantum superposition. Can multiple realities exist at once? The quantum world is a realm filled with uncertainty and possibilities at every moment. Quantum superposition is a phenomenon that challenges our understanding of reality and stretches the limits of our imagination. Although abstract and complex, it is fundamentally an astonishing concept that takes physics far beyond the reality we know. Superposition is the ability of a particle to behave as if it exists in multiple states at once. The easiest way to think about it is to imagine that a particle can be in one place and simultaneously in another. In the classical world, this is impossible. If an object is somewhere, it cannot be elsewhere at the same time. But in the quantum world, a particle can hold multiple possibilities simultaneously. As seen in Schrödinger's famous cat example, a particle or system can be in a state where it is both alive and dead until observed. This is both a contradiction and a sea of possibilities. Superposition creates a situation where all the unobserved potentialities of an object coexist in an unseen universe. A photon, for instance, may have a certain probability of being at a particular location, but in reality, it can exist in a superposition of multiple positions. Until we measure it, each of those possibilities is considered equally real. This principle points to the fact that the reality we perceive is very different from the underlying reality of nature. Quantum superposition reveals that the universe is multi-layered and pluralistic in nature. Reality is not a fixed, isolated event, but a whole where everything exists simultaneously and is interconnected. In the quantum world, everything is both a possibility and a reality, until an observer collapses those possibilities into a definitive outcome. Quantum entanglement. Is it possible to connect across vast distances? Quantum entanglement. Is it possible to connect across vast distances? In the quantum world, there are phenomena that stretch the boundaries of science, defy logic, and challenge our intuition. Quantum entanglement is one such phenomenon. It describes how two or more particles can be mysteriously connected, regardless of the distance between them. If the state of one particle changes, the state of the other changes instantly, as if there were no distance between them. But how is this possible? Is there some interaction that transcends the distance, time, or speed of light? In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen introduced the EPR paradox, Einstein-Podolsky-Rosen paradox, to provoke discussion on the strange and paradoxical nature of quantum entanglement. Entanglement links the properties of two particles, such as the spin of an electron, in such a way that when the state of one particle is changed, the other is instantly affected, no matter how far apart they are. Einstein referred to this as spooky action at a distance, because it contradicts the laws of classical physics. Quantum entanglement is a phenomenon that has no counterpart in the classical world. The idea that two particles can have their states connected, where observing one affects the other, challenges the limits of human reasoning. Yet, in the quantum world, these extraordinary connections are real. When we alter a property of one particle, the other appears to respond as if instantaneously. It may seem as if communication exceeds the speed of light, but this interaction is explained within the logic of quantum mechanics. This mysterious entanglement is one of the most fascinating and mind-bending aspects of quantum physics. In the universe, nothing is truly independent, even if it seems far apart. Perhaps the fundamental structure of the universe is a web where all particles, all possibilities, are interconnected. Everything exists in an entangled state. Quantum tunneling, the impossible path to overcoming barriers. Quantum physics is always filled with phenomena that challenge our imagination and defy conventional understanding. Quantum tunneling is one such concept that shows how it is possible to bypass physical barriers in ways that seem impossible. Under classical physics, a particle needs enough energy to overcome a particular obstacle. However, in the quantum world, particles can tunnel through barriers, indicating a possibility beyond the rules of classical physics. Quantum tunneling occurs particularly when dealing with subatomic particles. For example, if an electron doesn't have enough energy to pass through a potential barrier, the quantum tunneling phenomenon comes into play. Although the electron seemingly can't overcome the barrier, it can actually pass through or around it. This illustrates a mathematical interpretation of the probability that the electron can bypass the barrier. The electron's ability to surpass the barrier happens in a way that classical physics cannot explain, occurring as a quantum mechanical process based on probabilities. Quantum tunneling has significant technological applications, particularly in nuclear fusion processes, such as those that power the sun and in semiconductor technology. For example, the operation of transistors relies on quantum tunneling. Electrons pass through barriers within semiconductors, allowing devices to function properly. On a deeper level, quantum tunneling also reveals a fundamental nature of the universe that is not limited by mere observations. This phenomenon shows that physical barriers are, in essence, just probabilities and temporary obstacles. Reality is not entirely fixed. Everything can jump to another potential reality, as though passing through a tunnel. Many worlds, the universe of infinite possibilities. Quantum physics is a realm that constantly challenges our understanding of the fundamental nature of reality, often far beyond our intuitions. The many worlds theory is perhaps one of the most surprising and fascinating approaches to this strange world. It suggests that every event is simultaneously happening in multiple parallel universes, each with its own outcome. In other words, every choice, every observation, and every quantum event results in a new universe. What if every small decision we make actually creates a new universe? Developed by Hugh Everett in 1957, the many worlds theory offers an alternative explanation to the conventional interpretations of quantum mechanics. Traditional quantum theory posits that a particle can exist in multiple states at once, and when observed, one of those states collapses into reality. However, Everett proposed that instead of this collapse, each possibility creates a new parallel universe. So, when a decision or event occurs, in one universe, it might unfold one way, in another, it might unfold differently, but both outcomes exist in separate universes. According to this theory, we make choices, but only the reality we observe is definitive for us. In other universes, probabilities play out in different ways. Essentially, the many worlds theory suggests that every decision, every observation, every interaction leads to the creation of countless new universes. The universe we can observe is merely one branch, but beyond that, there are other universes with different possibilities continuing to exist. This idea stretches the boundaries of classical physics and reasoning. Reality, beyond a singular moment, exists across constantly branching and diverging universes. Each alternative reality is so close, yet different in ways we might never notice. Often, these different realities are not independent. Each is connected to another possibility. We may exist across many universes, all of them overlapping yet distinct. Quantum indeterminacy, the vanishing boundaries of reality. Quantum indeterminacy is one of the deepest and most mind-bending aspects of the quantum world. This concept describes a situation where a system enters an indeterminate state and cannot settle on a definite outcome without direct observation or interaction. Indeterminacy is a phenomenon that has no counterpart in the classical world, which assumes everything is fixed in some way or another. But at the quantum level, things work very differently. Here, everything is filled with probabilities, and the state of a particle or object does not become definite until it is observed. Quantum indeterminacy can be understood through Schrödinger's famous cat thought experiment. The cat being both alive and dead at the same time is an example of the uncertainty present in the quantum world. This indeterminate state exists until the observer interacts with the system. A system can exist in a range of different possibilities simultaneously, and only when observed does it collapse into a single reality. In other words, the outcome of a quantum system depends on whether we look at it or interact with it. This situation blurs the boundaries between physical reality and observation, leading to much deeper questions about the foundations of physics. Quantum indeterminacy offers a new perspective on the nature of the universe. In the classical world, we assume everything is clear and unchanging. But in the quantum realm, uncertainty is inherent to the system itself. Everything exists within infinite probabilities and indeterminate states, continuously evolving. A particle can only decide where it goes, or what happens once it is observed. This uncertainty challenges our perception of reality. Quantum indeterminacy reveals that reality may not be something that is fixed and shaped only in a single moment of observation. In fact, it may have a far more complex and mutable structure. Reversal of time, the mysterious boundary between past and future. Time is one of the most fundamental elements that shape each of our lives, something we consciously experience. However, in the quantum world, the nature of time is much more complex and surprising than the understanding we are accustomed to. The reversal of time is one of these extraordinary phenomena. According to classical physics, time only has one direction. We move from the past to the future. But in quantum mechanics, The idea that time can flow backward challenges our understanding of how the universe works. Time reversal appears as a statistical possibility within the framework of quantum mechanics. The direction of time is connected to the second law of thermodynamics, which states that entropy always increases and systems move toward disorder. However, at the quantum level, particles and systems can, under certain conditions, move backward in time. For instance, an electron may have the possibility to move in the opposite direction of its previous motion. Yet, such motion can only occur under very specific conditions and at the microscopic level. Time reversal is often associated with phenomena such as quantum tunneling and quantum indeterminacy. These events suggest that time can evolve in a nonlinear way that cannot be explained by classical physics. If time were to reverse, it would show just how fragile and relative the temporal sequence we are used to really is. A particle moving backward in time may not be possible in the classical sense, but at the quantum level, the probabilities are such that the linear progression of time itself can be questioned. The reversal of time is not just a theoretical concept. It also raises much deeper questions about the nature of the universe in both scientific and philosophical terms. Time at the level we perceive may seem like a continuous flow, but at the quantum level, there are signs that time has a far more complex and flexible structure. The idea of time reversal speaks to the fact that the universe may be filled with infinite possibilities, and that everything exists in a reality where anything can happen. Quantum teleportation, beaming information, not matter. The concept of teleportation, often seen in science fiction movies, is generally considered impossible by scientists. However, quantum physics is full of unexpected surprises, and what we're discussing here is not the classical idea of transporting an object from one place to another at the speed of light. Quantum teleportation refers not to the physical transfer of an object, but to the instantaneous transmission of its quantum state from one location to another. In other words, we teleport information, not matter. This phenomenon is made possible by a strange property of quantum mechanics called quantum entanglement. When two or more particles become entangled, they share a deep connection such that changing the state of one instantly affects the other, no matter how far apart they are. This is what Einstein famously called spooky action at a distance. Quantum teleportation utilizes this entanglement mechanism to transfer quantum information from one particle to another at a different location. How does quantum teleportation work? Quantum teleportation requires three essential components. A quantum particle to be teleported, for example, a photon or electron, two entangled particles A and B, classical communication, traditional signal transfer method. Here's how the process works. Suppose Alice wants to send a quantum state to Bob. Alice has a quantum particle whose state she wishes to copy onto Bob's particle. However, in quantum mechanics, direct copying of information is forbidden, no cloning theorem. Instead, Alice interacts her particle with one of the entangled particles and performs a measurement. This measurement destroys the original quantum state, but generates classical information that Alice can send to Bob via a conventional communication channel, such as radio waves or email. Using this classical data, Bob can manipulate his entangled particle to become an exact replica of Alice's original particle. Thus, quantum information is successfully transferred from one location to another. However, the original particle ceases to exist, meaning teleportation does not duplicate the particle, but rather moves its quantum state. Why is quantum teleportation important? Quantum teleportation holds immense potential for future technologies, especially in quantum computing and quantum networking, where information needs to be transferred securely and instantly. Quantum communication and security. It could enable an unhackable communication system, far superior to traditional encryption methods, quantum computers, By allowing ultra-fast data transfer between quantum processors, it could drastically enhance computational power information transfer. It could revolutionize space exploration and high data transmission fields. However, one crucial fact remains. Quantum teleportation cannot transport people or large objects like in Star Trek. Only quantum information is transmitted. This raises deeper philosophical questions about the nature of reality itself. If the universe is fundamentally built on information and wave functions, could we one day teleport not just data, but even consciousness itself? For now, quantum teleportation remains confined to individual particles, but it might be the first step toward a discovery that could completely redefine our understanding of the universe. Philosophical time paradox: the fragile boundaries of past, future, and reality. Time is one of the greatest mysteries of humanity. From the moment we open our eyes, we feel that time is constantly moving forward. But is this really a necessity? What if time is just an illusion? These questions have given rise to philosophical time paradoxes, some of the deepest thought experiments ever conceived. One of the biggest debates about time is whether it is linear or cyclical. Classical physics assumes that time flows like an arrow. The past cannot be changed, and the future is undetermined. However, quantum mechanics, relativity theory, and even certain philosophical arguments suggest that this linear understanding may not be entirely correct. If time is not absolute, paradoxes emerge. Famous time paradoxes. 1. The grandfather paradox. Can we change the past? Imagine you have a time machine and travel back to the past to kill your grandfather before he has children. If you succeed, you would never be born. But if you were never born, how could you have traveled back to the past in the first place? This circular contradiction highlights the complexity of causality, cause and effect relationships in time travel. There are two major solutions proposed for this paradox. Self-consistent universe model. Even if past interventions are possible, whatever happens must already be part of history. You may try to kill your grandfather, but you will always fail. The universe maintains consistency and prevents paradoxes. Many worlds theory. If you alter the past, you create a new parallel universe. Your grandfather dies in the new reality, but your original timeline remains unchanged. 2. Bootstrap paradox, a causal loop. Imagine a writer who wants to write a novel, but has no inspiration. One day, he travels to the future, takes a completed version of his book from his future self, and brings it back to publish in the present. But who originally wrote the book? This paradox suggests that time might be cyclical, allowing objects or knowledge to exist without an origin. If information or matter has no creation point, it raises profound questions about the fundamental nature of reality. 3. The relativity of time paradox. Einstein's theory of general relativity shows that time does not flow at the same rate for everyone. Gravity or velocity can alter time perception. For example, an astronaut spending 1 year near a black hole may return to Earth to find that centuries have passed. If time is not absolute, does it truly exist? If time depends on the observer's perception, are the past, present, and future real, or just an illusion? Some philosophers argue for the eternal now theory, suggesting that all of time exists simultaneously, and we merely perceive it as moving forward. Does time even exist? Since we don't fully understand time, philosophical time paradoxes raise deep questions about reality. Is time truly progressing, or do we just perceive it that way? If the past cannot be altered, do we really have free will? Is time an illusion or a fundamental aspect of the universe? Perhaps time is a vast, directionless structure, and we are merely beings who think we are moving in a straight line. Quantum philosophy and reality. How real is the universe? Our quest to understand the universe has long been based on the deterministic laws of classical physics. According to Newtonian mechanics, if we know the initial conditions of a system, we can predict its future behavior with certainty. However, in the early 20th century, quantum mechanics emerged as a revolutionary framework that challenged the very notion of an objective and absolute reality. Quantum physics suggests that the fundamental building blocks of the universe do not follow strict determinism. Instead, they behave according to probability and uncertainty. For example, rather than having a fixed position, an electron can exist in multiple places at once until it is measured. This leads to profound philosophical questions. What is reality? Does something exist if it is not observed? Is there a connection between consciousness and the physical world? These questions lie at the heart of quantum philosophy, an area that explores the implications of quantum mechanics for our understanding of existence, perception, and reality itself. 1. The Copenhagen interpretation. Does observation create reality? One of the most widely accepted explanations of quantum mechanics is the Copenhagen interpretation, formulated by Niels Bohr and Werner Heisenberg. According to this view, a quantum particle does not have definite properties until it is measured or observed. For instance, in the famous Double-Slit Experiment, electrons behave like waves when they are not observed, creating an interference pattern. However, when a detector is placed to observe them, they suddenly behave like particles. This suggests that the act of observation influences reality itself. This leads to a shocking idea. Does the universe exist in a definite state only when we observe it? A famous thought experiment that illustrates this paradox is Schrödinger's cat. If a cat is placed in a box with a radioactive atom that has a 50% chance of decaying and triggering a poison release, quantum mechanics suggests that until we open the box, the cat exists in a superposition of being both alive and dead at the same time. Only upon observation does it collapse into a definite state. This raises deep philosophical concerns. If reality is observer-dependent, what was the universe like before conscious beings emerged? 2. The many worlds interpretation. Do all possibilities exist? Another radical view is the many worlds interpretation MUI, proposed by Hugh Everett. Unlike the Copenhagen interpretation, which suggests that observation collapses possibilities into a single outcome, MUI argues that all possible outcomes occur, but in separate, parallel universes. In Schrödinger's cat experiment, this means, in one universe, the cat is alive ... In another universe, the cat is dead every time a quantum event occurs. The universe splits, creating infinite realities. If this is true, it has profound implications for free will, time, and consciousness. Do we truly make choices, or do we simply experience one of many possible outcomes? Are we just one version of ourselves, while infinite other versions exist in alternate realities? Is our universe just one of countless parallel worlds? 3. Quantum mechanics and consciousness. Is the mind part of reality? Some physicists and philosophers suggest that consciousness and quantum mechanics are deeply connected. This is because in quantum theory, the observer plays an essential role in determining reality. This idea, known as quantum consciousness theory, suggests reality is collapsed by conscious observers. Our minds may function on a quantum level. Consciousness is not just a byproduct of the brain, but a fundamental aspect of reality itself. Physicists like Roger Penrose and Stuart Hameroff have proposed that human consciousness arises from quantum processes occurring in microtubules within brain cells. If this theory is correct, it could mean that the mind is not separate from the physical world, but is deeply woven into the fabric of reality itself. 4. What is reality? An illusion or an absolute structure? The most fundamental question in quantum philosophy is Is reality truly real, or is it merely a construct of our perception? Some theories suggest that the universe is fundamentally a mathematical or informational structure, and that our experience of reality is simply a subjective interpretation of underlying probabilities. In this sense, quantum mechanics echoes the ideas of Plato's allegory of the cave, where we may only be perceiving shadows of a deeper, more complex reality that we do not fully understand. Conclusion: redefining reality. Quantum mechanics does not just help us understand the microscopic world. It fundamentally challenges our assumptions about existence, observation, and reality. It raises deep philosophical questions. Is reality absolute, or is it shaped by the observer? Is consciousness a fundamental part of the universe? Are time, space, and matter real, or are they just illusions? We may not have definite answers yet, but one thing is clear: quantum mechanics has forever changed our perception of the universe. To truly understand reality, we must first learn to question it. Quantum measurement problem: when does reality become real? Quantum mechanics is one of the most successful theories in explaining the behavior of subatomic particles. However, it contains a deep mystery about what happens when a measurement is made. This is known as the quantum measurement problem. 1. Quantum superposition and measurement. According to quantum mechanics, a particle, such as an electron, can exist in multiple states at once, a phenomenon known as superposition. This means that an electron is not located at a single point, but instead exists as a cloud of probabilities in different places. However, when we measure this particle, we always find it in only one definite location or state. The big question is, why and how do all possible states collapse into a single outcome when we measure them? 2. The mysterious process of wave function collapse. In quantum mechanics, the mathematical representation of a system state is called a wave function. Before a measurement, the wave function contains all possible outcomes. But the moment we measure it, all these possibilities disappear, and only one definite reality emerges. This process is called wave function collapse. However, physicists still do not fully understand why or how this collapse happens. 3. The Copenhagen interpretation. Reality depends on measurement. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, is one of the most widely accepted explanations. According to this view, quantum systems remain indeterminate until they are measured. When a measurement is made, the system's wave function collapses into a single state. Reality becomes definite only when observed. This radical idea is best illustrated by Schrödinger's cat thought experiment. If a cat's life or death depends on quantum superposition, does the cat exist in both states until we open the box? 4. Alternative explanations. How does reality collapse? Several alternative explanations attempt to solve the quantum measurement problem. Many worlds' interpretation, the wave function does not collapse. Instead, the universe splits into different versions, where each possibility happens in a separate reality. Hidden variables theory. There may be undiscovered rules governing quantum mechanics that determine the outcome before measurement. However, no such hidden variables have been found so far. Consciousness and quantum mechanics. Some theories suggest that conscious observation itself causes wave function collapse, implying that reality depends on a conscious observer. Conclusion: the quantum measurement problem remains a mystery. The quantum measurement problem is one of the greatest puzzles in physics. Is reality truly undetermined until we measure it? Or is there a deeper law of nature we have yet to discover? We may not have the answers yet, but one thing is certain: quantum physics has forever changed how we perceive the universe. Quantum decisions. Are we truly free? Do we make decisions with complete free will, Or are they influenced by hidden randomness at the core of the universe? Quantum mechanics challenges the deterministic nature of classical physics, suggesting that our decision-making processes may be shaped by uncertainty and probabilities. 1. Classical physics and determinism. Is the future predetermined? According to Newtonian physics, if we know the initial conditions of a system, we can predict its future with absolute certainty. This is a deterministic view of the universe. If our brain operates according to physical laws, then our decisions may already be predetermined. However, in the 20th century, quantum mechanics changed everything. In the quantum world, certainty is replaced by probabilities. 2. Quantum uncertainty. Are decisions truly random? Werner Heisenberg's uncertainty principle states that it is impossible to know both the position and momentum of a quantum particle at the same time. This means that in the quantum world, there is no absolute certainty, only probability waves. This has led to the idea that our brain might also function on a quantum level. If neural activity is influenced by quantum effects, then our decisions may not be deterministic, but probabilistic. 3. Quantum consciousness. Is our brain quantum? Physicists Roger Penrose and Stuart Hameroff proposed that human consciousness might arise from quantum processes in microtubules, tiny structures inside brain cells. According to this theory, decisions are not entirely predetermined, but may be shaped by quantum probabilities. Consciousness may not work like a classical machine, but as a quantum system. Free will could exist independently from classical physics laws, if true. This could mean that our choices are influenced by quantum randomness rather than strict determinism. 4. Many worlds interpretation. Do we make every possible decision? The many worlds interpretation suggests that all possible outcomes of quantum events actually happen, but in different universes. If this is true, every decision we make exists in multiple parallel realities. Each choice creates a branching path, leading to different versions of ourselves experiencing different results. Free will might not be about choosing one path, but experiencing all possible outcomes in different versions of reality. This radically alters the concept of free will. When we make a decision, all other possibilities also happen in alternate universes. We just experience one of them. Conclusion: quantum mechanics and free will. Quantum mechanics challenges the strict determinism of classical physics, suggesting that our decisions might be influenced by randomness and probabilities. But does this mean we are truly free? Or are we just guided by quantum randomness? We don't have a definitive answer yet. But one thing is certain: quantum mechanics forces us to rethink everything we thought we knew about decision-making and free will. Quantum and dreams. Where does reality begin and end? Dreams are one of the greatest mysteries of the human mind. They feel real, yet they are not bound to the physical world. Could quantum mechanics hold the key to understanding dreams? Modern science suggests that dreams are the result of electrical and chemical processes in the brain. However, quantum physics challenges our understanding of reality and consciousness. 1. Dreams and quantum superposition. Can two realities exist at once? In quantum mechanics, superposition means a particle can exist in multiple states at once until it is measured. Could waking up from a dream be similar to a quantum wave function collapsing? Are we stuck between two realities while dreaming? When dreaming, our brain disconnects from the physical world, but still creates vivid experiences. Perhaps this is a superposition-like state of consciousness. 2. Quantum entanglement and shared dreams. Are our minds connected? Quantum entanglement suggests that particles can remain connected regardless of distance. If consciousness operates on a quantum level, could humans be subconsciously entangled? Why do some people report shared or similar dreams? This idea hints that dreaming might not be just an individual experience, but possibly a connection to a collective consciousness. 3. Quantum uncertainty and dream perception. What is real? Heisenberg's uncertainty principle states that a particle's position and momentum cannot both be precisely known. Similarly, do we experience uncertainty in dreams, like in dreams within dream scenarios? Which reality is more defined, waking life or dreams? Perhaps consciousness is more classical in waking life, but behaves more like quantum uncertainty during dreams. 4. Many worlds and dreams. Are we seeing parallel universes? The many worlds theory suggests that every possible event happens in a different universe. If this is true, are dreams windows into parallel realities? Does consciousness shift to different worlds while we sleep? Some dreams feel like visiting unknown but strangely familiar places. Is this just memory recombination or something more? 5. Time and dreams. Are we experiencing quantum tunneling? In dreams, time flows differently. What feels like hours can pass in minutes. Could this be a form of quantum tunneling of consciousness? Is the brain shifting between time dimensions during sleep? This suggests that our perception of time in dreams might be influenced by quantum effects. Conclusion: dreams, quantum consciousness, and reality. While no definitive link exists between quantum mechanics and dreams, both challenge our perception of reality. Are dreams similar to quantum superposition? Is consciousness connected through quantum entanglement? Could the many worlds theory explain dream experiences? Science has yet to fully explain dreams, but quantum physics forces us to question reality itself. Maybe, just maybe, dreams are a doorway to something greater than we understand. Quantum communication, the unbreakable future of messaging. Traditional communication systems, from the internet to phone networks, face serious security risks. Cyber attacks, data breaches, and information manipulation have become major threats. But what if we could create a completely secure communication system? This is where quantum communication comes in, a revolutionary technology that uses the strange laws of quantum mechanics to make information exchange unhackable. 1. Quantum cryptography, unbreakable encryption. Today's encryption methods rely on mathematical complexity. However, with the rise of quantum computers, traditional encryption could soon become obsolete. Quantum cryptography, specifically quantum key distribution (QKD), changes the game by using the laws of quantum mechanics to guarantee data security, detecting any eavesdropping attempts instantly, ensuring that if a hacker tries to intercept the information, the system immediately shuts down. With QKD, we could soon have a hacker-proof communication system. 2. Quantum entanglement, instant information transfer. At the heart of quantum communication is quantum entanglement, a phenomenon where two particles remain connected no matter how far apart they are. Changing one particle's state instantly affects the other, no matter the distance. Some scientists speculate this could enable faster-than-light communication, although this is still debated. While quantum entanglement does not technically transmit classical information faster than light, it enables ultra-secure synchronization and coordination of data transfer. 3. Quantum Internet, the future of networking. Unlike today's Internet, which relies on classical signals, the quantum Internet would function using entangled photons for data transmission. Data is transferred securely without risk of interception. Any unauthorized access attempt is immediately detected. It enables real-time, ultra-secure data sharing. Some key benefits: unhackable data security, super-fast quantum data transfer, a new era of ultra-secure global communication. Governments and tech companies worldwide, including China and the US, are investing heavily in space-based quantum communication to make this vision a reality. 4. Challenges and the future. Despite its promise, quantum communication faces some challenges. Quantum states are extremely fragile. Maintaining entanglement over long distances is difficult. The technology is still expensive and complex. However, with ongoing research, quantum internet might soon become a reality. Conclusion: the ultimate secure communication. Quantum communication is set to redefine data security and internet technology. Unbreakable encryption. Ultra-fast quantum data transfer. The future of the internet, quantum internet. If we dream of a truly secure, hack-proof internet, quantum communication could make that dream come true. Quantum minds, bridging consciousness and quantum physics. Consciousness is one of the most profound and complex mysteries of the human mind. While we perceive the world, produce thoughts, and make decisions, we still do not fully understand how we experience this conscious reality. However, modern scientific theories, like quantum mechanics, offer new and exciting approaches to explaining the nature of consciousness. So, how can we define quantum minds? The theories exploring quantum minds suggest that the processes of thought and conscious perception in the brain may occur at the quantum level. This presents a radically different perspective from classical neuroscience, which traditionally asserts that the brain functions through chemical and electrical processes. Quantum minds propose that quantum events at the microscopic level could be the foundation of our consciousness and mental processes. 1. Quantum consciousness, quantum interactions in the brain. Quantum consciousness is a theory that explores how the fundamental principles of quantum mechanics might influence conscious thought processes. According to this theory, certain cells and particles in the brain may interact at the quantum level. These quantum processes in the brain could potentially create multiple states of consciousness, connecting conscious and unconscious minds in novel ways. Quantum superposition phenomena might enable the brain to process several different thoughts simultaneously and allow for new connections between conscious and unconscious states. Quantum entanglement could potentially create connections between different conscious states, allowing various aspects of consciousness to be linked at a quantum level. Quantum consciousness challenges the traditional boundaries of understanding how our brains work. It offers a way to comprehend mental processes that are much deeper and more intricate than we previously imagined. 2. Quantum minds and the unconscious, deep connections. Another fascinating approach to understanding quantum minds merges unconscious processes with quantum interactions. Similar to Carl Jung's idea of the collective unconscious, quantum entanglement may link thoughts, emotions, and memories that exist in the unconscious. If these interactions are happening at the quantum level, then perhaps the layers of the mind, the conscious thoughts and unconscious impulses, are more deeply and mysteriously connected than we think. 3. Quantum superposition of mental states. Quantum superposition refers to the phenomenon where a particle can exist in multiple states at the same time. Applied to mental processes. A person may experience multiple emotions or thoughts simultaneously, with these thoughts existing in different layers of the mind at once. Quantum processes in the brain could potentially allow for multiple alternative realities in the mind, where different possibilities and thoughts coexist. Our conscious mind may not simply exist in one fixed reality. Instead, a wide range of thoughts and possibilities might exist simultaneously in a mental superposition state. 4. Quantum minds and universal consciousness. Some quantum theorists advocate for the idea of universal consciousness, suggesting that all conscious beings, and possibly the universe itself, are quantumly interconnected. If consciousness truly operates at the quantum level, then our thoughts and experiences could be intrinsically linked to a universal network of consciousness. This idea could be associated with phenomena like telepathy, collective experiences, and shared perceptions, where minds are interconnected in a way that goes beyond space and time. This universal consciousness theory proposes that quantum processes might be responsible for creating a unified field of awareness that connects all living beings, perhaps even the entire cosmos. Conclusion: the future of quantum minds. Quantum minds may offer a new lens through which to explore the profound nature of consciousness, thought, and reality. This fresh approach to understanding the brain goes beyond traditional neuroscience, revealing how quantum interactions might play a role in shaping our mental experiences. Understanding the quantum processes behind consciousness could unlock answers to the deepest questions about the nature of thought and awareness. The theories of quantum minds have the potential to revolutionize philosophical, scientific, and technological fields alike. While we have not yet fully understood the connection between mind and consciousness, quantum science offers a new hope in unraveling these mysteries. Perhaps the answers to our most profound questions lie within the quantum interactions of the mind. Symmetry in the universe, the hidden code of cosmic balance. When we look deep into the universe, we discover a perfect order hidden within chaos. The spirals of galaxies, the intricate patterns of snowflakes, and even the structure of atoms, all of these are shaped by the laws of symmetry. But what exactly is symmetry, and how does it manifest in the fundamental fabric of the universe? What is symmetry? Symmetry is a property of a system or structure that remains unchanged after a certain transformation, such as rotation, reflection, or translation. In everyday life, we see symmetry in mirror reflections, the arrangement of flower petals, and the wings of a butterfly. However, symmetry is not just a feature of art or nature. It is deeply embedded in the fundamental laws of physics. Symmetry in physics, the hidden order of nature. Modern physics relies on symmetry principles to describe the fundamental laws of nature. Scientists have discovered that all physical laws are governed by symmetry. Some key examples include translational symmetry. The laws of physics remain the same regardless of where you are in the universe. For example, gravity works the same way on Earth as it does on Mars. Rotational symmetry. If an object or system is rotated and still looks the same, it exhibits rotational symmetry. The spherical shapes of planets and their rotations are examples of this. Time symmetry. The laws of physics do not change over time. This means that the same physical principles that governed the early universe still apply today and will continue to do so in the future. These symmetries create predictability and order in the cosmos. Symmetry and its breaking, the birth of the universe. At the moment of the Big Bang, the universe started in a state of perfect symmetry. However, as the universe expanded and evolved, this symmetry broke, giving rise to the fundamental forces and particles we see today. One of the most significant symmetry breaks was between matter and antimatter. Initially, they existed in equal amounts, but a tiny asymmetry allowed matter to dominate, leading to the formation of galaxies, stars, and planets. If this symmetry had never broken, the universe would be an empty void, filled only with energy. Symmetry in biology, the blueprint of life. Symmetry is not limited to physics. It also plays a crucial role in biology and living organisms. The human body exhibits bilateral symmetry, 2 eyes, 2 ears, 2 arms. This symmetry helps maintain balance and coordination. DNA itself follows a symmetrical helical structure, allowing genetic information to be stored and transmitted efficiently from the smallest cells to the largest ecosystems. Symmetry helps maintain the stability and order of life. Symmetry in art, a universal aesthetic rule. Artists, architects, and musicians have long recognized that symmetry plays a key role in beauty and harmony. In architecture and painting, the golden ratio is widely used to create visually appealing designs. Music follows mathematical symmetry in rhythm, melody, and harmonies, creating patterns that are pleasing to the human brain. This suggests that symmetry is not just a physical principle, but also an essential part of human perception and creativity. What happens when symmetry breaks? Interestingly, if everything were perfectly symmetrical, life as we know it would not exist. The breaking of symmetry is just as important as symmetry itself, as it creates diversity and complexity in the universe. Without symmetry breaking, atoms could not bond, preventing the formation of molecules. Stars and galaxies would never have formed. DNA, the blueprint of life, would not have taken shape. This means that both symmetry and its breaking are essential for the existence of the universe. Conclusion: the universe is written in the language of symmetry. Everything in the cosmos, from the vast galaxies to the smallest subatomic particles, follows a delicate balance of symmetry and asymmetry. Symmetry provides stability, while its breaking allows change, complexity, and life itself to emerge. From the unique shape of a snowflake to the grand spiral of the Milky Way, the universe is a masterpiece crafted by the poetry of symmetry. Time and reality, the hidden fabric of existence. Time. Is it an unstoppable, inevitable force flowing endlessly? Or is it just a product of our perception? Does reality really exist, or is it an illusion shaped within time? Time and reality are two of the greatest mysteries of the universe. These two concepts may seem simple and unchanging in daily life, but modern physics, philosophy, and consciousness studies present a much more intriguing picture. Time, absolute or relative? Traditionally, we imagine time as a river that flows in one direction. The past, present, and future are clearly separated. However, Albert Einstein's theory of relativity revealed that time is, in fact, not absolute, but relative. Time is affected by mass and velocity. For example, if a spaceship approaches the speed of light, time inside it slows down. So for an astronaut, several years could pass while on Earth. Hundreds of years may have passed. Mass can bend time. Large celestial bodies bend spacetime, slowing down the passage of time. That's why time moves slower near a black hole. This shows that time is not an absolute reality, but a perception dependent on our location and speed. Reality, a product of our mind. Is reality a model presented to us by our senses, or is it a fundamental structure that exists independently? Quantum physics suggests that a particle does not have a definite position or velocity until it is observed. This means reality is determined by the observer. Our brains do not directly perceive reality. We construct a model of the world through our eyes, ears, and nervous system. So, the world we perceive is actually a simulated version created by our brain. This brings up the idea that reality could be a hologram shaped by our minds. The connection between time and reality. If time is not absolute and reality changes with observation, how are these two concepts related? Does the present moment really exist? According to quantum physics, the past and future are uncertain and only gain meaning once observed. Time could be a byproduct of reality. Some theories suggest that time is not a real entity, but rather a process perceived by conscious beings. This leads to the idea that the universe could be timeless in nature. Alternative realities in the multiple faces of time. If time is truly an illusion, could it be that multiple realities exist simultaneously? The quantum many worlds theory suggests that at every decision point, the universe splits, creating different realities. Dreams and altered states of consciousness may be alternative realities. While dreaming, our minds lose track of time and dive into different realities. This reinforces the idea that both reality and time may be merely a perception. Conclusion: matter and the void are complementary. In the quantum world, matter and the void form an inseparable pair. Matter exists as a sea of probabilities shaped by observations, while the void is an infinite source of energy. These two concepts, which shape each other, define how the universe works. Perhaps understanding the relationship between matter and the void brings us closer to understanding the true nature of the universe. Quantum biology, the connection between life and the quantum world. Biology traditionally focuses on the structure, function, and evolution of living organisms. However, in recent years, scientists have begun to explore the connections between quantum physics and biological processes, unveiling the concept of quantum biology. This branch of study looks at how quantum mechanical effects influence life and its functions, potentially offering insights into some of nature's deepest mysteries. Quantum superposition. A particle can exist in multiple states simultaneously until observed. This concept may play a role in biological molecules processes like binding or separation during cellular functions. Quantum entanglement. Quantum entanglement is a phenomenon where particles, no matter how far apart, instantly influence each other. This could be significant in biological processes, especially in signaling and interactions between cells. Some known examples in quantum biology. Several biological processes exhibit quantum phenomena, which can be explained using principles of quantum mechanics. Here are some examples. Photosynthesis and quantum superposition. Photosynthesis is the process by which plants convert light energy into chemical energy. Recent studies suggest that plants can use quantum superposition and quantum transitions to absorb light energy more efficiently. This allows plants to collect light photons simultaneously through multiple pathways, improving energy capture. This phenomenon reveals the important role quantum effects can have in biological processes. Plants can utilize quantum mechanical abilities to capture maximum energy from sunlight. Magnetic field sensing, quantum physiology in animals. Certain animals possess the ability to sense magnetic fields. For example, some birds and whales navigate using the Earth's magnetic field during migration. This extraordinary ability can be explained by quantum entanglement and other quantum effects. Studies suggest that a specific molecule in animals' eyes responds to Earth's magnetic field, allowing them to navigate using quantum mechanical properties. The role of quantum biology at the cellular level. Another area of interest in quantum biology is how quantum particles interact within cellular processes. How do quantum effects guide the activities of cells? Enzymes and quantum tunneling. Enzymes are proteins that accelerate biochemical reactions. Some of these reactions can happen faster due to quantum tunneling effects, where particles pass through barriers that would otherwise block them. This can speed up reactions and allow biological systems to function more rapidly. DNA repair and quantum effects. The process of DNA repair involves fixing errors in cells' genetic code. Quantum biology suggests that quantum effects may be involved in the repair process. Specifically, electron transfer and quantum tunneling could play a role in repairing DNA molecules accurately. The future of quantum biology, new horizons and potentials. Although quantum biology is still in its infancy, it could open up new avenues for biotechnology and life sciences research. In the coming years, quantum biology might help us gain deeper insights into the fundamental workings of life. Here are some potential future developments. Quantum computing and biological research. Quantum computers could be powerful tools for modeling biological systems. This might lead to breakthroughs in genetic engineering, drug development, and molecular biology. Artificial enzymes and quantum tunneling. Thanks to quantum biology, we might develop artificial enzymes that use quantum tunneling to catalyze chemical reactions more efficiently, benefiting medical treatments and therapies. Quantum biology sheds light on the mysteries of life. Quantum biology takes a unique perspective by examining biological processes through the lens of quantum mechanics. From photosynthesis to magnetic field sensing, from cellular repair to quantum tunneling, many biological phenomena appear to rely on quantum effects. As research in this field continues to grow, we might one day understand life at its most fundamental level, leading to significant advancements in biotechnology and human health. Quantum philosophy and existence, a journey into the depths of reality. Quantum philosophy explores the deep connections between quantum mechanics and existential questions. While quantum mechanics seeks to understand the fundamental laws of nature through the behavior of subatomic particles, philosophy deals with profound questions about human existence, consciousness, and reality. When these two domains intersect, concepts like reality, observation, time, free will, and being are re-examined. Quantum philosophy goes beyond understanding the physical laws of nature. It also aims to understand human existence, consciousness, and our place in the universe. So, how is the quantum world related to existence? Let's delve into how the philosophy of quantum mechanics intersects with existential questions. Quantum mechanics, observation, and reality. Quantum mechanics presents strange and paradoxical behaviors in nature. One of its oddities is the role of observation in determining reality. Quantum physics asserts that particles can exist in a superposition of states before being observed. For instance, an electron can exist in multiple states simultaneously until observed, at which point it takes a definite form. This leads to a deep philosophical question. What is reality? In the quantum world, things are not real until observed. Without observation, a particle can exist in multiple forms. This uncertainty suggests that reality itself may be indeterminate before observation. This raises profound questions about existence and the nature of consciousness. In the quantum world, observation becomes a crucial factor in shaping reality. But what does this mean for our everyday perception of reality? How does human consciousness fit into this uncertain and dynamic world? Quantum philosophy and the nature of time. Another important concept in quantum philosophy is the nature of time. In quantum mechanics, time is treated differently from classical physics. Some quantum theories even suggest that time could flow backwards. In quantum mechanics, when particles interact at a specific point, time may not be strictly linear. This introduces an existential inquiry. How real is time? If time is not just a conceptual framework, then how clear are the boundaries between past, present, and future? Quantum philosophy suggests that time might not be a natural flow, but may actually be shaped by conscious observation. This invites us to reconsider the relationship between being and time. Quantum waves and consciousness, philosophical reflections. Quantum mechanics shows that particles can behave as waves. This concept leads to reflections on the nature of consciousness itself. Could consciousness, like a quantum wave, be a phenomenon that spreads and changes form? This raises the question of whether consciousness has a universal nature, or if it is solely confined to individual beings. Philosophically speaking, the relationship between consciousness and existence becomes tangled with the notions of free will and reality. How much does human consciousness intertwine with quantum uncertainty? Does consciousness exist in a superposition state, or is it always sharply defined? These questions propel us to deeper philosophical investigations about existence. Quantum philosophy and universal connections. Quantum philosophy also highlights the idea that everything in the universe is interconnected. Quantum entanglement suggests that two particles can be so deeply linked that a change in one will instantaneously affect the other, no matter how far apart they are. This interconnectedness supports the idea that everything in the universe is related. If everything in the universe is connected at the quantum level, it prompts us to question the meaning of human purpose. Our existence, our conscious observations, and our decisions are all interwoven with everything else. Quantum philosophy offers us the perspective of a holistic universe, where all things are linked. Quantum philosophy and the meaning of existence. Quantum philosophy offers new perspectives on the nature of reality, consciousness, time, and existence. Quantum mechanics helps us understand the fundamental laws of nature, but it also raises existential questions. The relationships between reality, observation, time, consciousness, and the universe are deeply intertwined in the quantum world. Quantum philosophy challenges us to reconsider our understanding of existence, consciousness, and our place in the cosmos. It encourages us to explore how everything is connected and to reconsider the nature of reality as not just a physical phenomenon, but as something deeply philosophical. These reflections may guide us to a deeper understanding of our purpose and our relationship with the universe. Quantum time travel, a journey to the past and the future. Time travel has long been a popular theme in science fiction. With H.G. Wells' The Time Machine, it became a staple of literature and cinema, inspiring many films and shows. However, quantum mechanics and modern physics may bring this once impossible idea closer to reality. Quantum time travel offers a perspective based on the fundamental laws of the universe and provides deeper insights into the nature of time. But is it really possible? Quantum time travel differs from traditional notions of time travel. Quantum mechanics suggests that time may not be linear, and under certain conditions, it might behave in ways that defy conventional expectations. The concept of time in quantum mechanics is deeply tied to the relationship between space and time itself. So how does quantum mechanics connect to time travel, and can it truly be possible? Let's explore these questions further. The quantum nature of time, uncertainty, and superposition. Quantum mechanics goes beyond classical physics and investigates the most fundamental levels of nature. Within this framework, uncertainty and superposition play roles that may impact the way time functions. In the quantum world, particles can exist in states that are both present and absent, or in many different states at once. This concept could extend to time itself, where particles may exist in multiple timelines or evolve across different moments in time. The non-linearity of time could be a result of quantum theories. While time appears to flow in one direction in our everyday experience, quantum mechanics suggests this flow may not always be straightforward. The idea of time travel is closely linked to the notion that past and future might not be as separate as they seem. A quantum particle could potentially exist in multiple time frames, extending across both the past and the future. This opens up new dimensions of time beyond traditional understanding. Quantum entanglement in time travel. Quantum entanglement is a phenomenon where particles are so deeply connected that any change to one particle will immediately affect the other, no matter the distance between them. This challenges classical ideas of distance and time. If a particle can be influenced by another, no matter how far apart they are, it suggests that time itself might not be as fixed as we think. In the context of time travel, quantum entanglement could theoretically create connections across different times. If entangled particles can communicate instantaneously across vast distances, could they also interact across different points in time? The concept of entanglement might serve as a potential link for time travel. Closed time-like curves in time travel. As we think further about quantum mechanics and time travel, the concept of closed time-like curves (CTCs) comes into play. This idea, related to Einstein's general theory of relativity, suggests that time can bend back on itself, creating a loop in which a time traveler can return to a previous point in time. Quantum mechanics also proposes scenarios where time travel could be mathematically possible. If quantum particles' movements across time could be analyzed, it might be possible to solve the paradoxes of time travel. Closed time-like curves provide a potential mathematical foundation where time travel loops back on itself, allowing travel to the past, Philosophical and practical aspects of time travel. The concept of quantum time travel doesn't only involve physical theories. It also raises philosophical questions. If a person could travel to the past and change an event, how would it affect the future? Famous paradoxes like the grandfather paradox come to mind. If you went back in time and altered your grandfather's life, would you still exist? Quantum mechanics could help resolve these paradoxes with theories such as multiple universes or parallel timelines. Perhaps time travel doesn't change the past, but creates a new history in a parallel universe. This makes quantum time travel not only a scientific concept, but a philosophical one as well. The potential of quantum time travel. Quantum time travel remains a theoretical concept filled with uncertainties and unknowns. However, quantum mechanics provides a framework with a nonlinear nature of time, along with concepts like entanglement, suggests that time travel may one day be more than just a science fiction fantasy. Time travel may still seem like a distant dream, but quantum mechanics reminds us just how mysterious and profound the universe is. Perhaps understanding the true essence of time will require us to transcend both physical and philosophical boundaries. Quantum reality and wholeness, the fundamental structure of the universe. Quantum mechanics is a theory of physics that helps us understand the laws governing the most fundamental aspects of the universe. However, one of the most fascinating aspects of this theory is the unusual and sometimes mind-bending perspective it offers on the nature of reality. Quantum theory not only explains the behavior of particles, but also raises deep philosophical questions about the workings of the entire universe. One of the most intriguing questions is how the concepts of reality and wholeness come into play in the quantum realm. The interactions between the fundamental building blocks of the universe, such as atoms and particles, not only defy the predictions of classical physics, but also contradict our daily observations. Yet, this paradoxical situation actually shows that the universe has a much deeper and more interesting structure. In the quantum world, everything operates within a wholeness. Particles may appear independent, but they are, in fact, part of a much larger interconnectedness. What then is quantum reality, and how does it form a sense of wholeness? Let's embark on a deeper exploration. The foundation of quantum reality, superposition, and uncertainty. In quantum mechanics, reality is not as we perceive it in the classical sense. Concepts like superposition and uncertainty reveal that reality has an elastic and multi-layered nature. A particle does not exist in just one place or state. It can exist in multiple states at once. For instance, an electron can be in different locations simultaneously, but when observed, only one state becomes real. This superposition suggests that reality does not follow a single linear path, but instead moves through multiple possibilities. However, these possibilities only collapse into a definitive outcome once observed. Thus, quantum theory tells us that reality is intrinsically uncertain. When we observe an event, a choice is made between the different possible outcomes. Wholeness and interconnectedness, quantum entanglement. In the quantum world, everything operates within a wholeness. Quantum entanglement is one of the key indicators of this interconnectedness. When two particles are entangled, no matter how far apart they are, changing one will instantly affect the other. This means that the particles are deeply connected. The universe is, in a sense, an interconnected web. Quantum entanglement transcends classical concepts of distance and time, showing that particles are part of a larger, universal connection. This link helps us understand the invisible workings of the universe. The existence of quantum entanglement emphasizes the fact that every part of the universe is a part of a whole. This may not only be true for quantum particles, but for the entire universe. Quantum reality and consciousness. Another fascinating aspect of quantum reality is its relationship with human consciousness. Quantum theory also reveals how the observer shapes reality. The Copenhagen interpretation, for example, suggests that when a particle is observed, it collapses into a specific state. This shows that the observer and the observation are deeply connected. Consciousness plays a unique role in the quantum world. Our minds interpret the quantum realm through observations. This reveals that reality is not just a physical phenomenon, but also a conscious experience. Quantum mechanics not only helps us understand the fundamental structure of the universe, but also raises important questions about the relationship between reality and consciousness. Philosophical and practical dimensions of quantum reality. The quantum view of universal wholeness is not only a physical idea, but also has a philosophical dimension. If everything is part of a whole, then everything in the universe has a connection and balance. This brings up an existential question. What is the relationship between humans, nature, and the universe? If everything is part of a whole, are we simply reflections of the entire universe? From a philosophical perspective, reality and wholeness may not be singular entities, but rather holistic experiences. Quantum theory tells us that everything is interconnected, and that the universe is not just the sum of individual parts. This raises deep questions about what it means to exist in a universe where all things are interconnected. Quantum reality and wholeness. Quantum mechanics turns everything we know about the universe upside down. Reality is far more complex and layered than we perceive it. Superposition and uncertainty show us that reality exists in a state of constant possibility, while entanglement and wholeness illustrate the interconnected nature of everything. The quantum world not only helps us understand the mysteries of the universe, but also challenges us to rethink our relationship with it. Understanding the fundamental structure of the universe and the concept of wholeness provides both scientific and philosophical insights. Quantum mechanics helps us connect our conscious experiences with the workings of the universe, enabling us to perceive a reality far more intricate than we ever imagined. Physical reality and the observer, a universal connection. Physical reality can be defined as the world we see, touch, and experience around us. However, fields like quantum physics reveal that physical reality is composed of much deeper and more complex structures. In classical thought, the observer and the observed object are considered separate and independent. But in the quantum world, this distinction becomes blurred in a complex manner. An observer does not just observe the universe, but also plays a role in shaping it. Quantum mechanics shows that the observed reality can change depending on the observer, affecting the fundamental structure of the physical world. So, what is the relationship between physical reality and the observer, and what role does this play in our understanding of the universe? Let's begin exploring this question from the perspective of quantum mechanics. Physical reality, classical and quantum approaches. Classical physics assumes that the universe is composed of objects that exist independently of observation. Objects are found at specific locations and times, and these objects continue to exist without changing when observed. For example, a table remains fixed in its place, and we cannot change its position or properties by merely observing it. In classical reality, the observer is an external entity to this reality. However, with quantum mechanics, this understanding changes dramatically. At the quantum level, observations and observed events are not independent of each other. One of the fundamental principles of quantum theory, superposition, suggests that a particle can be in multiple states at once. For instance, an electron can be in different locations simultaneously, but once observed, it collapses into a specific location. This means that observation shapes the reality of the universe. The observer effect, the quantum measurement problem. Quantum mechanics suggests that the observer plays a role in shaping the physical reality of the universe. The quantum measurement problem questions how the state of a quantum system is determined when observed. Before an observation, the state of a quantum system consists of many possibilities. For example, an electron may exist both in one location and another. However, once the observer measures the system, it collapses into a single state. This means that observation directly shapes reality. The Copenhagen interpretation is the most famous approach to explain this. According to this theory, until observation, a particle can exist in multiple places at one superposition, but once observed, this situation ends and a single reality is determined. This situation is a striking example of how the observer shapes the reality of the universe. Observer and reality, interdependence. In quantum mechanics, the boundary between the observer and the observed event becomes increasingly blurred. Quantum phenomena like entanglement cause the state of one particle to be dependent on another. When two particles are entangled, no matter how far apart they are, changing one instantly affects the other. This shows how connected every part of the universe is. But this connection is not limited to particles alone. The observer is an integral part of shaping the reality of the universe. The decisions made by an observer can determine quantum events. This shows that there is an interaction between the observer and the observed, and this interaction forms reality. Thus, the observer is not just an external observer of the universe, but an active participant in its formation. Philosophical implications: the relationship between reality and the observer. The relationship between physical reality and the observer raises deep philosophical questions, not just scientific ones. Quantum mechanics, by suggesting that the observed reality is shaped by the observer, raises existential questions about the concept of reality. If the observer affects the reality of the universe, is everything in the universe a reflection of the observer? Or is reality entirely based on the conscious experiences of the observer? Some interpretations of quantum theory link the role of the observer to the fundamental structure of the universe. This brings philosophical ideas like idealism into the discussion. Idealism suggests that consciousness or thoughts create the external world. Quantum mechanics presents a perspective that questions how consciousness and observation influence our understanding of the fundamental structure of the universe. Reality, the observer, and universal connection. Physical reality in quantum theory becomes a dynamic structure shaped by observations. The observer plays an active role in not just observing, but also shaping the formation of reality. Quantum mechanics shows us that the relationship between the observer and the observed shapes the fundamental structure of the universe. The understanding that the universe is a dynamic structure shaped by the observer presents profound questions both scientifically and philosophically. The relationship between reality and the observer helps us understand how both concepts are interrelated and how they can impact our understanding of the universe. Thank you for listening this far. I hope you enjoyed the video. Don't forget to share your thoughts in the comments.